Welcome back to the Deep Dive, where we take your source material, your research, your notes, your biggest cosmic questions, and we cut right to the core of what you need to know.
Mm.
Today, we are really undertaking a true deep dive into a topic that I think constantly challenges the limits of human cognition. We are exploring the edge of the universe.
It's a spectacular dive because, the moment you start talking about the edge of the universe, you're already challenging a concept most of us just internalize from childhood.
Right.
The idea of infinite, unending space.
Exactly. And that initial fundamental question, it's often attributed to the 19th century German astronomer Heinrich Olbers, and it's so simple, it's brilliant.
Olbers paradox.
Olbers paradox.
Mm-hmm.
If the universe truly stretches on forever and it's filled with stars and galaxies, then why, when you look up at the night sky, is it black?
Right. Logically, it should be blindingly bright.
Mm.
The combined light from an infinite number of sources should just light up the whole sky, day and night.
But it doesn't.
And that paradox is the perfect entry point for today. Because that blackness, that void you think you see beyond the stars, it's not the edge of the universe itself.
Yeah.
It marks an edge, for sure, but it is the boundary of our perception. It's the absolute limit of where information in the form of light has actually had time to reach us.
So our mission today is to unpack this triple conspiracy, how the finite speed of light, the history of cosmic time, and the accelerating expansion of space all combine to create a fixed, measurable boundary for us, for the observer.
And that ancient light we find at that boundary, as we'll get into, is the absolute key to understanding the entire universe's creation and, well, its fate.
And central to this deep dive is resolving what has to be one of the most stunning paradoxes in modern astrophysics.
It's a big one.
Our sources confirm the universe is only, 13.8 billion years old?
That's our best number, yes, derived from the very light we're talking about.
Yet the distance to the edge of what we can see is demonstrably 46.5 billion light years?
Right.
How does light travel 46.5 billion light years in only 13.8 billion years? It feels like it shouldn't work.
It feels like it breaks the most fundamental rule. And that discrepancy forces us to rethink the very fabric of reality itself.
Okay, let's unpack this immediately. Before we get into the mind-bending physics, we need to define the scale of our bubble, our current measurable, comprehensible bubble of space. What is the scope of what we're actually allowed to see?
We have to start with the measurable, which we call the observable universe.
Yeah.
And it's crucial to understand this is a defined mathematical construct, not just some vague idea.
And while that idea of a measurable universe seems to contradict infinite space, our source material gives us some very concrete, specific dimensions for this cosmic bubble.
It does. Based on everything we know about the expansion rates since the Big Bang, the observable universe is a perfect sphere of space. Its total diameter is approximately 93 billion light years across.
93 billion. That number it's almost meaningless in human terms.
It's staggering.
It's a sphere that has hundreds of billions of galaxies, each with hundreds of billions of stars. And crucially, this sphere has a very immediate sort of personal implication for every single person listening.
Yes, and this is the beautifully bizarre part of the concept.
Yeah.
You are right now located exactly in the center of it.
I am the center of my own universe.
You are. The observable universe is defined by the light that has had time to reach you. So we are all at the center of our own individual observable universe. The distance from us right now out to the edge of that sphere, it's about 46.5 billion light years, expanding out in every single direction.
Okay, before we go any further, and I know our audience is very informed, but we have to spend just a moment clarifying the light year. It's so central to everything.
Absolutely. A light year is purely a unit of distance. It's just the distance light travels in one Earth year, nothing more.
Not time, distance.
Distance. And the reason this measurement is so fundamental comes straight from Einstein and his establishment of the constant speed of light. It's a cosmic speed limit.
The famous...
It's exactly, see. Light moves through space at a constant rate, and nothing made of matter, no information, can ever move through space faster than that speed. That's the rule.
Okay.
So when we say the edge is 46.5 billion light years away, we are saying light has traveled that distance since its creation.
So inside that massive 93 billion light year sphere, that's everything. Everything we have ever known or will ever know. Every star, every structure, every piece of information that has had time to travel to us since the universe began.
And this bubble defines the full reach of our fundamental empirical knowledge. Anything beyond that 46.5 billion light year limit. Even if it exists right now, we simply cannot see it.
Why not?
Well, either the light from it just hasn't had enough time to reach us yet, or, as we're going to prove later, the space between us is accelerating so fast that the light can never, ever close the gap.
It forces a moment of reflection, doesn't it? When you look up and you see maybe a few thousand stars with your naked eye, you have to remember you were sitting at the core of a bubble 93 billion light years wide.
It's an incomprehensible scale, but it's mathematically defined.
And that definition leads us perfectly into our next segment, where we tackle that blackness in the night sky, what we've called the Great Deception. That blackness you see when you look out into the void, it is not empty space. It is not an absence of light. It is actually light that our eyes simply cannot detect.
The edge of our observable bubble is, in fact, a wall of light.
A wall of light.
It's the most ancient light imaginable. It's the first light that ever emerged from the hot, dense, opaque soup that was the universe in its infancy. Just moments after the Big Bang.
Okay, so if this light is all around us coming from the furthest edge, why is it black? Why isn't it that blinding glow Olbers predicted?
This is where we have to move past the simple visible spectrum and talk about light aging. The concept of stretching waves, or what we call wavelength redshift.
Let's use that analogy we talked about before, the ripple on a pond.
It's a good one. Think of light as waves traveling through the medium of space. If you drop a pebble, that's your light source, into the pond, you get these tight, energetic waves right around the impact point.
High-frequency light, blue or ultraviolet.
Exactly. But here's the key distinction. The wave isn't just traveling through the water. The water itself is expanding, and it's stretching the wave as it goes. As that light wave travels across vast, expanding cosmic distances, the space it occupies physically stretches, pulling the wave apart. This increases the distance between the wave peaks, which lowers its energy and shifts the light toward the red end of the spectrum.
That's redshift.
That's redshift. And when that light wave stretches past the visible spectrum, it transitions into lower energy ranges. First, it moves into infrared.
Infrared, we're familiar with that. Heat signatures, night vision goggles.
Right. It's the heat our bodies give off. But the light from the earliest galaxies, even when it enters the infrared spectrum, is incredibly faint because of the sheer distance it's traveled. Billions and billions of light years.
Which is why we needed to build something like the James Webb Space Telescope.
Precisely. JWST was engineered specifically to detect deep infrared light far beyond what our ground-based instruments or even the Hubble could manage.
So with Webb, we can penetrate a big chunk of that blackness.
We can. It lets us capture the faint red-shifted light from galaxies that formed incredibly early in the universe's history, maybe just a few 100 million years after the Big Bang. It truly sees almost everything that is formed inside our observable bubble.
But, and this is a big but, our sources confirm that even this pinnacle of engineering has a limit. Even beyond the most distant, earliest galaxies JWST can photograph, there is still that black void.
It still can't see the absolute edge.
No.
And that's because the light from the very first moments of the universe has been stretched so severely by the continuous expansion of space that it's moved completely past the entire infrared range. It's redshifted beyond even JWST's capabilities.
So we have light that is traveling for billions of years. It's getting stretched until it's invisible to our best instruments. How do we make the leap from seeing the limit of Webb to confirming this wall of light actually exists?
We have to dive even deeper into that pond of stretched light, far beyond infrared, into the lowest energy band possible for light.
Which is?
Microwaves.
And we're not talking about the appliance in the kitchen.
No. Definitely not. We're talking about light waves so faint, so stretched out, that they appear to us as an incredibly weak, totally uniform signal of background radiation. It's like a persistent static that fills the entire cosmos, coming at us from every possible direction.
And this leads to one of the most famous and kind of funny discovery stories in modern science. It was an accident.
A total accident. We're talking about the cosmic microwave background, or CMB, and it was discovered in 1964 by two radio astronomers, Arno Penzias and Robert Wilson, at Bell Labs in New Jersey. They were using this huge, sensitive horn antenna.
For satellite communication, I think.
That's right. And they kept picking up this persistent, annoying, low-level background noise.
A hiss.
And they tried everything to get rid of it. Everything. They spent months recalibrating the antenna, checking all the wiring. Yeah. They even, and this is the famous part, removed what they called a white dielectric material from inside the horn.
Which turned out to be pigeon droppings.
It was pigeon droppings. They thought that was causing the interference, but nothing worked.
It was literally just noise they couldn't explain.
And what makes this so incredible is that they found the noise was perfectly uniform no matter where they pointed the antenna.
Day or night, summer or winter.
Exactly. They eventually realized they were detecting a faint signal that wasn't from Earth, wasn't from the sun, it wasn't even from our own galaxy.
It was coming from everywhere.
Everywhere. This signal was the thermal radiation left over from the Big Bang. About 380,000 years after the Big Bang, the universe finally cooled enough for atoms to form, and that allowed photons' light to travel freely for the first time.
And that is the first light of the universe.
It is. And after 13.8 billion years of expansion and stretching, it has become that faint microwave hiss Penzias and Wilson found. It is the literal wall of light at the edge of our observable universe.
The CMB, the ultimate proof of the Big Bang model. But their discovery was just a hiss. When we see those famous, colorful maps of the CMB, the blue and yellow splotches, we're looking at something much more detailed.
Absolutely. The Penzias and Wilson discovery showed uniformity. But the later missions, like the COBE satellite in the 90s, then WMAP, and finally the Planck satellite, they are what created those incredibly detailed color maps.
And to be clear, those maps aren't showing color, they're showing tiny temperature variations.
Precisely. They are heat maps. They show incredibly slight variations in the microwave frequency and therefore temperature. We're talking variations of maybe 1 part in 100,000 Kelvin. The blue and yellow are just visualizations of those tiny hot and cold spots.
And what does that heat map instantly tell us about how the universe began?
It tells us that the universe is not, and never was, perfectly uniform. If the Big Bang had been a completely smooth, even expansion, the CMB map would just be one solid color. But the splotches, those areas of slightly higher and lower density, are crucial.
They're the seeds.
Yes. The slightly cooler, denser areas acted as gravitational seeds. They were the initial scaffolding around which matter eventually clumped together over billions of years.
So those high-density areas
Became the clusters of galaxies we see today, surrounded by the great cosmic voids that correspond to the slightly less dense, hotter areas on the CMB map. It's a literal fossil record of the universe's structure when it was less than 500,000 years old.
Okay. So we've established the scale, 93 billion light years across. We've identified the boundary as the CMB, the first light. Now we use that boundary to get to the central conflict of this deep dive.
Age versus distance.
Exactly. The precise measurement of the CMB's properties gives us a highly accurate age for the universe, or at least for the first light that defines our horizon.
And that age is 13.8 billion years old.
Okay, so let's stack the variables. Age of the light, 13.8 billion years.
Correct.
Distance that light has traveled, 46.5 billion light years.
Correct.
And the fundamental rule, nothing travels faster than light.
The math is impossible under standard assumptions. It just doesn't work. If light is traveling at the cosmic speed limit, then the edge of the universe should be 13.8 billion light years away, period.
So that enormous, inexplicable gap between 13.8 and 46.5 billion means something profound and totally unexpected is happening to space itself.
It is.
And to understand that, we need a bit of a history lesson. We have to go back to the early 20th century and the giant who tried to create the perfect cosmic framework, Albert Einstein.
Einstein was developing general relativity, his theory linking gravity, time, and space. It was a complete revolution. But when he applied his theory to the entire universe, he fell victim to the prevailing belief of the time.
Which was that the universe was static.
A static and uniform structure, an unmoving, eternal sea of stars. It was a philosophically comfortable idea.
But his own math contradicted it.
It did. General relativity showed that gravity is always an attractive force. So if you have this infinite static distribution of matter, gravity should immediately start pulling everything together. The universe should collapse.
So a static universe was impossible according to his own theory.
It was dynamically unstable. But Einstein was so committed to the idea of stasis that he fudged the numbers.
It did.
To prevent this gravitational collapse and force his math to give him a static model, he introduced a new, arbitrary variable into his equations. He called it the cosmological constant.
And this constant was basically a desperate fix.
It was a total invention, a repulsive force, a kind of anti-gravity that he said existed in empty space. Its only purpose was to perfectly counterbalance the attractive force of gravity and keep the universe in perfect unmoving balance.
And the incredible irony, which we have to stress, is that he later called this the biggest blunder of his career because he missed predicting cosmic expansion. But he was fundamentally right about the force itself.
He was right for the wrong reason. He was trying to enforce stasis, But in reality, the force he invented was enforcing a dynamic, ever-changing cosmos. The constant was actually much stronger than gravity.
So while Einstein was fighting to keep the universe still, across the Atlantic, Edwin Hubble was starting his career, and he was about to blow the static model to pieces. But he couldn't have done it without a crucial astronomical tool.
No. He needed the Cepheid variable star, and the key research there was done by Henrietta Leavitt in the early 1900s at the Harvard College Observatory.
Why are Cepheids so important?
They are nature's perfect ruler. Leavitt discovered that these stars pulse. They brighten and dim in a regular cycle. And she found a fundamental relationship. The longer it took the star to complete its pulse cycle, the intrinsically brighter the star actually was.
The absolute luminosity.
Exactly. So once you calibrate that relationship, you can look at any Cepheid anywhere in the cosmos, measure its pulse rate, and know its true brightness.
And that's the key. If you know how bright a light source actually is, and you know how bright it appears from Earth, you can calculate the precise distance to it.
And that is exactly what Edwin Hubble did with what they called the Andromeda Nebula. Until then, everyone assumed these nebulas were just dust clouds or star systems inside our own Milky Way.
So Hubble spots a Cepheid in Andromeda.
He does. And his calculation, based on its long, slow pulse, told him the star had to be an absolute powerhouse, incredibly bright. But when he looked at it through his telescope, it was incredibly dim.
The only way to resolve that is distance.
A vast distance. The conclusion shattered the worldview. Andromeda was not a cloud of dust in our system. It was a gigantic collection of stars, completely separate from our own. It was the first hard proof of a galaxy.
Wow.
And that instantly replaced the idea of a uniform sea of light with a universe made of massive, faraway clusters, separated by immense, previously unimagined distances.
The universe just got a lot bigger.
Far, far bigger. And that cleared the way for Hubble's next, even more monumental breakthrough, proving that space itself is dynamic.
And he built on the work of Vesto Slipher, who had already noticed that the light from these distant galaxies was redshifted.
Slipher noticed they were all shifted toward the red end of the spectrum. But he didn't have the distances. Hubble put the two pieces together, the distance he calculated with the Cepheids, and the recession speed he calculated using that redshift.
Let's just quickly refresh the Doppler effect for light.
Sure. The classic analogy is an ambulance siren. As it approaches you, the sound waves compress, so the pitch is higher. As it recedes, the waves stretch, and the pitch gets lower.
Same thing with light. Moving toward us is a blue shift, waves compress. Moving away is a red shift, waves stretch.
And Hubble's fundamental discovery, what we now call Hubble's law, was a clear linear relationship. The further away a galaxy was, the faster it was moving away from us.
Which gave us two non-negotiable clues.
Two clues that completely destroyed Einstein's static model. One, space is expanding. And two, that expansion appears to be accelerating over time.
And that brings us right back to dark energy, the engine of acceleration. Einstein's static universe is dead. We now know that the universe isn't just expanding, it's speeding up, so we have to go back to that cosmological constant, that invented anti-gravity force.
The force is real, but its purpose was totally misunderstood. It wasn't there to balance gravity. It is demonstrably stronger than gravity. It's the dominant force in the universe driving everything apart.
And today, we call this overwhelming force of expansion dark energy, the energy that's just inherent in empty space itself. But how did we confirm it was accelerating? Hubble showed it was expanding, but the acceleration proof came much later.
It did. That came in the late 1990s, and it required a new tool. The Type Ia supernova.
The standard candles?
The best standard candles we have. A Type Ia supernova happens when a white dwarf star in a binary system steals material from its companion until it hits a critical mass.
The Chandrasekhar limit.
Right. And once it hits that limit, it explodes with a consistent maximum brightness. Every single one.
So, just like the Cepheids, we know their absolute luminosity, which makes them perfect, very distant measuring sticks.
And in the late 90s, two independent research teams started tracking these distant supernovae. They measured their apparent brightness to get the distance and their redshift to get the speed.
And what they found was shocking.
The expectation was that maybe the distant supernovae would appear brighter than predicted if gravity was slowing things down. But they found the opposite. The distant supernovae were consistently dimmer than expected.
Dimmer means further away.
Exactly. The light from these distant objects had been traveling for so long that the space between us and them had expanded way more than any model predicted. The universe wasn't slowing down, it was speeding up dramatically, driven by this mysterious dark energy.
That's the empirical proof. So what is the mechanism here? What does dark energy actually do?
Its mechanism is, it's beautifully self-reinforcing. Dark energy is a property of the vacuum of space itself. The key concept is, the more empty space you have between two galaxies, the more dark energy is generated in that volume, which pushes them apart even faster.
So it's an engine that gains power the more it runs. Expansion creates more space, which creates more dark energy, which creates faster expansion.
And this is how we finally resolve the original paradox. 13.8 billion years of age, 46.5 billion light years of distance. The solution is in how we define motion.
Okay, there's a critical distinction between two types of velocity.
Yes. First, there's peculiar velocity. That's the motion of an object through space, like the Earth orbiting the Sun. Einstein's speed limit applies strictly to peculiar velocity. Nothing can move through space faster than light.
But then there's the motion of space itself.
And that is the Hubble flow, the motion of objects being carried away from each other by the expansion of space. Space itself plays by different rules. The Hubble flow is not restricted by the speed of light.
This is superluminal expansion.
Superluminal expansion. This is the crazy loophole that keeps Einstein's rule for matter intact, but still solves the paradox.
So the light itself never broke the speed limit.
Never. The light that defines the edge of our bubble emerged 13.8 billion years ago and traveled at the constant speed of light the entire time. That rule was never violated. But during those 13.8 billion years, the space that contained that light accelerated outward because of dark energy.
The light kept running at Sia, but the racetrack itself was stretching out from under it.
Exactly. It was stretching and accelerating, creating that final 46.5 billion light-year distance.
And this explains the fundamental limit of our knowledge. Galaxies beyond that boundary are receding from us faster than light right now.
They are. The light they emit today will never ever reach us. The gap is widening too quickly.
So as dark energy continues to accelerate, our observable horizon is. It's constantly shrinking relative to the total size of the universe. What we see today is the most information we'll ever get.
It's a slightly terrifying thought.
Yeah.
But for now, we move on to the final major correction we need to make.
Right. Now that we understand the scale and the forces, we have to let go of that simple but deeply ingrained picture of the Big Bang they taught us in school.
The cosmic egg.
The cosmic egg, or the infinite point of density that exploded like a grenade into empty space.
That analogy is fundamentally flawed. It implies a singular center, a point of origin in space. It's an easy mental picture run the expansion backwards, everything collapses to one spot. But the evidence proves that's wrong.
And the evidence, once again, is the CMB, that bubble that surrounds us.
If the universe had expanded from one location, then the center of the CMB sphere we see would be that point of origin. But we see the CMB surrounding us in a perfect sphere coming from all directions. And any observer anywhere in the universe would see the exact same thing.
So the conclusion, which is incredibly difficult to visualize, is that the Big Bang did not happen in one place.
It happened everywhere to everything all at once. It was an instantaneous phase transition of the entire cosmos, a sudden change in the state of all space and time.
Which leads us to the most rapid phase of expansion, the one that solves some of the biggest puzzles in cosmology.
Inflation.
Inflation refers to that tiny, tiny sliver of a second right after the Big Bang where the universe just expanded exponentially, faster than we can comprehend.
The magnitude of this expansion is what solves two major problems. Let's start with the horizon problem.
The horizon problem. What is that exactly?
When we look at that CMB heat map, the temperature is almost perfectly uniform across the entire sky. But if you look at one side of the sky and then the opposite side, those two areas are so far apart that light from them has never had time to travel to one another and even out their temperature. They've never been in causal contact.
They shouldn't be the same temperature. It's like finding two perfectly identical rooms in separate hotels that have never communicated.
The only way that works is if, before the CMB was released, the entire observable universe was packed into a tiny, tiny volume where all parts were in causal contact, where they could even out their temperature.
And inflation solves this by providing the mechanism that stretched that tiny uniform volume into the vast one we see today.
Exactly. Inflation took that tiny smooth area and expanded it faster than light, preserving that thermal uniformity while creating the enormous distances we measure today.
And the second puzzle it solves is the flatness problem.
Right. This is about the geometry of space. General relativity allows for space to be curved like a sphere, or curved like a saddle, or flat. And the math shows that if the universe started with any curvature at all, that curvature should have increased dramatically over time.
But when we measure the geometry of space today, it appears almost perfectly flat.
Inflation, again, provides the elegant solution. Imagine you have a balloon with a slight curve. As you inflate that balloon to an enormous size, any small section of its surface will appear flatter and flatter.
Okay.
The instantaneous superluminal expansion during inflation stretched the early universe so thoroughly that any initial curvature was effectively smoothed out, leaving us with the almost perfectly flat geometry we measure today.
So inflation is the mechanism we need to explain why the CMB is so uniform and why the universe appears flat. And it also explains the just mind-boggling scale of the Big Bang itself.
The scale is the hardest part. Our sources give a stunning example to try and wrap our heads around it.
Okay.
During that moment of inflation, which lasted less than a trillionth of a second, an area of space the size of a single grain of sand might have expanded to the size of an entire galaxy.
A grain of sand to a galaxy in an instant.
Now, hold that scale and connect it back to the happened everywhere concept. Try to imagine every single grain of sand in a huge sandbox expanding simultaneously to the size of a galaxy. All at once. That's what we're talking about.
It wasn't an explosion into space, it was an explosive expansion of space itself.
Driven by forces we still don't fully understand.
This journey has been foundational. We started by defining the scale of the observable universe, 93 billion light-years across, and recognizing that the observer is always at the center.
We navigated that paradoxical conflict between the universe's age, 13.8 billion years, and its physical distance, 46.5 billion light-years.
We identified the edge of our perception as the cosmic microwave background, detailing its accidental discovery and the crucial information hidden in its tiny temperature fluctuations.
We then traced the history from Einstein's blunder, the cosmological constant, to Hubble's empirical proof of expansion.
And we solved the age-distance paradox by differentiating between peculiar velocity motion through space, bound by light speed, and the Hubble flow, the expansion of space, which is unbound, all driven by dark energy.
And finally, we corrected that fundamental misconception of the Big Bang, shifting it from a localized explosion to an instantaneous phase transition that happened everywhere, solving the horizon and flatness problems with inflation.
It's just a testament to human ingenuity. Just by measuring that faint, stretched microwave light from the very edge of what we can see, we've been able to deduce the driving forces, the age, and the creation mechanism for the entire cosmos.
Indeed. And for a final provocative thought for you to take away, consider this. If the Big Bang happened everywhere all at once, and we are at the center of our observable sphere, the space beyond our 46.5 billion light-year horizon must be just as vast and complex as our own.
Right.
That unobservable universe is filled with observers who are also at the center of their 93 billion light-year spheres. Given the accelerating expansion, there are objects we see today that are already moving away from us superluminally. What does it mean for reality that the universe contains an ever-growing volume of galaxies and information that are already and permanently beyond our reach, a vast cosmic frontier that will become forever inaccessible, locked away by the very engine of expansion?
A knowledge horizon that is shrinking every second, an ocean of infinite, isolated reality. Thank you for joining us on this deep dive into the farthest reaches of reality.